Welcome back, Stanley Lake, podcast 14.2, so the second in our chemical kinetics investigations. So what we've seen so far is that you can establish the order of a reaction, whether it's first order, second order, zero order, with respect to a reactant from graphical representations of the experimental data. We've looked at the law of, method of initial rates as a way to figure out what the rate order is. However, when you start to look at the graphs a little bit more closely, the concentration versus time, because that's what rate is, change in concentration over time. Concentration time graphs don't really lead to a pretty clear distinction between first order and second order. So instead, we've got to look at rate concentration graphs. With the help of calculus, we're going to be able to use some different equations, or rather different laws, to help us figure out whether something is first order or second order or zero order, and then in turn kind of take a look at what that graph might look like for concentration versus rate. So there are two different types of rate laws. The first one is called the differential rate law. And this is the most common. This is the one that when we talk about rate laws, we're really talking about the differential rate law. And the other one is the integrated rate law. And if you're in calculus, those two words should sound very familiar to you. But like I said before, the good news is you don't actually have to use the calculus. You just got to know that, hey, it's a really good thing, and this is what it's based on. So the differential rate law is what we're going to kind of focus on first here. Differential rate law is used to show how rate kind of depends on concentration. If it's zero order, and what we've sort of seen before, this is, when we write the rate law, if it's zero order, your concentration is going to be raised to the zero power, which is 1. So really your rate law is just going to look like that. Rate equals K, whatever your constant is. If it's first order, let's say this is a little bit of a review from previous podcast, K to the first power, that's how it's called a first order reaction. Second order reactions, and then second order is your rate is K to the second power, so that's the second order. So again, a little review, but just so you know, this is called the differential rate law because you're comparing rate and concentration. On the flip side, when we have an integrated rate law, with the integrated rate law, we are doing a plot of concentration, I'm just going to abbreviate that, versus time. So we're looking at concentration at any given time. So what we do is you take the integral, I'm not saying that right, integral of the differentiated rate law. So with the zero order, since you're plotting your concentration of A versus time, and if you drew a graph with this, your graph, okay, we're going to put A over here, put time down here in seconds, your graph kind of looks like that, a straight line. So you could figure out, if you kind of remember what the rate law would look like, this one's pretty easy. We already get a straight line with this, and really the slope of your line is giving you your rate constant, K. This should be a C. I don't know what I was trying to say. There we go. Okay. First order. With a first order reaction, we're going to plot the natural log of the concentration of A versus time to get a straight line. Because if we plotted just plain old concentration versus time in seconds, with a first order reaction, the graph kind of looks like this. And that's a little hard to figure out what the slope of the line is, because the slope of the line is giving us our constant. So if we take the natural log of that, this is going to give us a line that looks just like this. And that's a whole lot easier to deal with when you're trying to figure out the rate. So what this means is this kind of changes our equation to look like this. We're going to take the natural log of A, which is equal to negative K, notice that we have a negative slope of our line, times T, plus the natural log of our original concentration, A to the 0. That means initial concentration. And if you kind of think about it, really this follows your fabulous graph y equals mx plus b, where m is your slope and x is time and y is your rate. So if you have your graphing calculator, you can use that to solve the equations also. Second order reactions. We're going to plot 1 over the concentration of A versus time. Reason being here, again, if we plotted concentration versus time, we're usually in seconds here, the second order reaction is going to look kind of like the first order reaction, but it sort of goes like this. So when we take the integral of that, I can't even say that, integral, we'll just go with that. It gives us a line that looks like that. Okay? So then our new equation is 1 over the concentration of A equals K, so we got a positive slope this time, times T, plus 1 over our initial concentration, A to the 0. So let's take a look at an example. Using the method of initial rates, we could figure out what the rate law is, but how do we do it with an integrated rate law using these other things? Well, again, everything is based on data. So what I'm going to show you is, hopefully, using the calculator, we're going to do some linear regressions. So if you haven't done these steps before, just kind of follow along. We're going to make a table. Usually you have a data table. And then I'll kind of show you what buttons to push if you haven't done this before. And remember that the slope of your line is going to be your value for K. Alrighty, so let's get started with an example. And I'm going to pull up my handy dandy little calculator so you can follow along and see how I'm kind of pushing the buttons as we do that. So I'm going to move that right there. So these instructions work for a bunch of different TI models. If you have something where these buttons aren't familiar, go ask Miss Humphreys. Hopefully you already know how to work that part. Okay, determine the rate law and the value of K with units for the reaction, and we've got N2O5. Now you see we've got our data table of information there. Ooh, where'd my calculator go? Why'd that go away? Okay. We've got our data table here. So now we're going to enter this information into our calculator. So first thing we're going to do is we're going to hit stat. Let me get the actual pen here. We're going to do stat. Okay, now I got it. Stat. We're going under edit and I'm going to hit enter there. So now I'm going to enter my information into these different lists. So we've got L1 and L2. So I'm going to enter in L1 the times. So I'm going to look at my times. I got 0. Go to the next one, 50. Not 51, 50. 100. 200. 300. So I'm just entering my time into the first list. Okay. Into my second list here. Come on. Second list. Into my second list, I'm going to put concentration. So I'll look at my table and put in my concentrations, 0.011, and then 0.07, am I doing that? 0.07, there we go, 0.0500, 0.025, 0.0125. I know there's zeros at the end, but it chops them off, it doesn't matter. Okay, so now I got my L2. Going to go to L3. Oops. L3. So you kind of want to be up here where L3 is highlighted, if you guys can see that. And I'm going to type in the equation natural log. So where the natural log is, right there. So I'm going to click natural log of L2. So if you kind of look at, if you see kind of down here where you see right above the number 1 and the number 2, I'm going to do that L2. Close my parentheses, enter, very good. Okay, now I got to do the same thing for L4, but in L4 I'm going to enter 1 over L2, L2, enter, and now I got some data. Okay, so now I can go to quit. Stat calc, so I'm going to push stat. Go to the calc. I'm going to scroll down until I see linear regression. Hit enter. And so now I got to tell it what what's the correlation I want it to make. So for the first one, I'm going to do L1, comma, L2, and see what I get. All right, so here's our equation, y equals ax plus b. You want to look at the r value. Okay, I'm going to try that again because I was supposed to have an r value. All right, so I got natural log 1, sorry, natural log L1, L2. Enter. There we go. Now I got the r value. I didn't have the diagnostic running on this thing yet. Okay, so we want to look at the r value. We want to look at the r squared value. The closer it is to 1 or -1, the straighter line is going to be. 0.88, that's not quite close enough. So I'm going to have to go back and let's do this again. So we're going to go stat, over to calc, down to linear regression, enter. This time I'm going to plot L1, which is our time, versus L3 and see what that gives us. Notice our R value is 0.999. So that's looking pretty darn good to me. I kind of like that one. But just to be sure, let's try the third one. Go back to my stat, calc, linear regression, and we're going to do L1, which is our time, and L4. Okay, my R squared value is 0.88. So that tells me that the one that I want for this to take place is where I'm plotting L1 and L3. L1 versus L3. So that gives me a linear regression of 0.999. And if you kind of remember what happened with L3 is we were plotting the natural log of our concentration of A. So that tells me that my equation that I'm going to use is Ln is this one. Oh, for my calculator, where's my calculator again? My calculator, I forgot to write down my R value, or the slope of my line here. So let's go back and figure out what that was. L1, L3, not L6, L3, here we go. Okay, from this it gives me my slope of the line. Your A value is your slope of the line, so that's 0.0069. So I'm going to go ahead and plug that in for my K value times T plus the natural log of A sub 0. And now so there's my rate law. Now what are my units going to be for K? We can kind of do a little dimensional analysis and figure that piece out. But that's how you figure out what the rate law is. One other snazzy feature of first order reactions is this idea of half-life. On your graphs, since we're doing concentration versus time for a first order reaction, you can figure out what the time is that it takes for a concentration of reactant to decrease by half of its original value. And so that's kind of known as half-life, where it ties nicely in with nuclear chemistry and the like. So how do we use half-life calculations? All right, so let's go through this example here. First order reaction is 35.8% complete. Calculate the rate constant. So the first thing I want to do is just kind of write out my rate law. Negative KT plus the natural log of A sub 0. Now I have some helpful pieces of information in here. Put some brackets around there so you know it's concentration. I know my concentration of A. If it's 38.5% complete, we're going to assume it's out of 100% of stuff. So that is my concentration of A. I'm going to be solving for my rate constant T. I know my time, 480 seconds. And natural log of my initial concentration, like I said, we're going to assume we got 100% of the stuff. So there you go. Now we can go ahead and solve for K. And so I came up with, and doing a little dimensional analysis as well, to figure out my units, seconds to the -1. So there's my value for K. Letter B, calculate the value of half-life. So if you have a half-life equation, and usually the one that you're going to see for first order, it looks something like this. T to the 1/2 means half-life. And for a first order reaction, it's 0.693 divided by K. That's the equation that we're going to use. So let's plug and chug. We've got our T, 0.693 divided by K. We just solved for our K value up there. And so the half-life would be at 346.5 seconds. So, letter C. Give myself a new screen so I got some room here. How long will it take for the reaction to go to 25%? So if my reaction is at 25%, that means I've got 75% remaining. And if I take a look at D and E also, if it's at 75%, that means I've got 25% remaining. And 95% means I got 5% remaining. So that's going to kind of help me as I use these different calculations. So let's take a look at letter C. How long will it take for the reaction to go to 25%? So I got to use my natural log of A, K to the T, using my integrated rate law here. Now my concentrations. What I'm going to do is kind of rearrange this equation, because really what I'm trying to solve for is T. So first I'm going to take care of my concentration. So I'm going to rearrange this equation here. Oops, not A to the 0, just A. Okay. Divided by A to the 0. There we go. Plug in some numbers. Negative, because these first order reactions have a negative slope, 0.00 T equals natural log of 75 over 100. I did it this way since I got two natural logs, and I can just kind of easily solve from here. So T will equal 144.4 seconds. Letter D. I'm going to do the exact same sort of setup. So as I said before, if you've got 75% gone, that means you've got 25% remaining. So that's my concentration of A. My initial concentration is still 100. My K value is still 0.002 times T. Go ahead and solve for T, and I get 693 seconds. 95% remaining means I have, 95% completion means I've got 5% left out of the original 100. Negative 0.002 T. My T is equal to 1,497 seconds. Alright, so that brings us to the end, and this is a very handy little table. Unfortunately, it's not in your textbook, so I stole this from somebody else, but it's a really great little reference tool to start wrapping your brain around what are all the different ways that we can calculate rates of reactions, whether it's zero order, first order, or second order. True, there's a third order, but it is rarely on the exams, so I would just focus on these. Alrighty guys, have a great day, and we'll see you soon.